We know that a handheld fixed magnet like this and a copper coiled wire together can produce an electrical current. But how exactly does it happen? If you want to know, then keep watching, because I'm going to explain now. The fixed magnet has a north and a south pole, and its magnetic field is orientated just like so, with the flow running through the centre and out like this. And this magnetic field on the fixed magnet is constant. It's always there, it always exists, meaning it's never turned on or off, it's always on. And that's exactly what's needed to fulfill its job. So then, we have the fixed magnet, and here's the copper wire. In order for it to produce an electrical current, it needs to be coiled round like this. And that's because when the fixed magnet's magnetic field speedily passes the coil, it has instant access to more of the wire's length. So another way of saying it is that more of the wire is exposed to the magnetic field. Therefore, it can affect more of the wire in one instance. And what that effect is exactly is all about what the copper coiled wire is made of. Simply put, billions and billions of copper atoms. And it's the structure of copper atoms that makes it so good at reacting to a magnetic field to create an electric current. And to understand how this happens, we need to take a look at the basic structure of the atom itself. So what's it made of? Well, in its centre nucleus there's 29 positively charged protons. And in there amongst them are 35 neutrons, called neutrons because they are neutral in charge, meaning they're neither positive nor negative. So basically, this 29 positive particles and 35 neutral particles makes up the centre nucleus of the copper atom. But remember, at the moment, we've only got positive charge here, because the neutrons aren't negative charge, they're no charge. And so what does it do? Well, it attracts the equal proportion of its opposites, so it attracts 29 negatively charged electrons. This now means that the atom has equalled out its own charge, so it's neither too negative nor too positive. This is known as a stable atom. And that's because it's got all the particles it needs. It doesn't need to attract anything. It's wholesome. And so all of these 29 electrons are constantly orbiting round and round the nucleus, and they never stop. And if you notice, all 29 electrons there are existing at different levels. And in fact, like all atoms, each level has a specific number of electrons. And so with copper atoms, there are always 2 electrons at this lower state closest to the nucleus. And at this level, the electrons are said to be at their ground state, so at their lowest level of energy. And that's because these are the 2 most drawn in to that positive pull of the nucleus. Being at this level, it means that the pull towards the nucleus is at its strongest. And this force means that there's a certain amount of drag for the electrons, so they can't quite move as quickly and as erratically as the other electrons. And as we go outwards to the other levels, each level has less of a drag, less of a force pulling it into the nucleus, and the more freedom to move quicker and more erratic the electrons have. So that means that these 8 electrons have more freedom to move, and these 18 electrons have even more freedom to move. All of which while still being caught up in the electrical pull of the nucleus. So they're all in the nucleus's orbit, just moving at different paces. And that brings me on to the highest level, and the reason I wanted to explain everything so far, because it's this level that occupies just 1 electron, which is the reason the copper wire can produce an electrical current. And that's because this one outer electron, having the least amount of attraction to the nucleus and therefore the least amount of drag, can behave in a way that's more erratic than all of the other electrons. And to better explain that, let's take a look at how these atoms make up the copper wire and how the electrons behave within it. Okay, so here's some copper wire, and in reality there'd be many billions and billions of atoms making up the wire. But so we can see things a little better, I'll bring it in so that we can see each atom. Okay, so we have our copper atoms and the all-important outer electrons, which I shall highlight. It's important to say now that the atoms don't orbit the nucleus in this uniformed way like this. they actually do so more like this, like a swarm of bees buzzing around, so it makes more of a cloud as they move somewhere near the speed of light. And of course each level is doing the same, and the further up we go, the more erratically they're doing it, until we get up to the one electron at the highest level which is moving the most freely. And whilst these electrons in these first three levels, caught up in that electrical pull of the nucleus, stay local to the nucleus, this lone electron at the outer level with the least pull doesn't stay local. It moves about from one atom to another. And that of course means there isn't one outer electron doing this from one atom, there is billions of them doing it, all at the same time. So that means, with billions and billions of outer electrons moving round and round from atom to atom at something like close to the speed of light, there's a constant sea of electrons surrounding all of the atoms, and this is indeed called the electron sea. And at the moment, these electrons are moving everywhere, backwards and forwards, side to side, and what's needed to create an electrical current is to put some order in there, and have them move together in one direction. And that's where the magnetic field of a fixed magnet comes in. Because when the magnetic field on the fixed magnet passes over the coil, the electrons inside the copper wire react to the magnetic field in such a way that the magnetic field pushes them all in one direction. So they're no longer moving randomly in different directions, they're all uniformly moving together. So each time the magnetic field passes the coil, it moves those electrons forward inside the coil. And because all electrons are negative in charge, they're all repelling each other. So as some electrons are being pushed forward by the magnetic field, those electrons that are being pushed forward repel the electrons in front of them, and that pushes those forward, a bit like the flow of a river. When the water's moving, it's pushing the water in front of it downstream. And this flowing movement of electrons is indeed what we refer to as an electrical current. And so in this instance, the electrical current is created by those outer electrons moving in one direction from each of those copper atoms. So basically, this is how a fixed magnet and copper wire can create an electrical current. I hope you enjoyed this video, and if you really feel it's been of some benefit to you, please consider giving me a thumbs up and subscribe. And please take a look down in the description where I've got some links to some of my other videos which you might find interesting. And so this is how this system works to the best of my knowledge and beliefs. Please do take a look at the disclaimer at the start of this video and down in the description. But for now, I want to thank you so much for watching, and I'll be back soon.